All right, physics time. We're talking today about, well, we're continuing our discussion about circular motion, but this one we're going to call rotational dynamics. I think that's a cute word for this. Rotational dynamics. We're talking about the way things change, dynamics, as they rotate, or the things that can change about things as they rotate. Remember, we had this idea of torque. Would you define torque for me briefly? Let me grab my ticket. Yeah, so it's the product of force times lever arm that produces a force over, I shouldn't use the word over, a force applied to I'm going to put in quotes, lever arm that produces a rotation, some change in rotation. It changes the rotation. So just like force caused acceleration, which is a change in linear motion, torque causes rotational acceleration, which is a change in rotation, which is a change in circular motion. Yeah? So we have these two parallels where it's force causes acceleration, changes linear motion. Torque causes, angular or rotational acceleration, which changes circular motion. And remember, we had this parallel going back a ways further when we had talked about centripetal forces, too. So torques cause or change rotation. The kind of classic example is if I have, and the reason we use the term lever arm, even though it's a circle and we kind of think of levers as straight things, so how does a lever apply to a circle? Well, we think of this idea of a simple lever with some load here and some load here. We'll call this load X and this load Y. What direction will a force applied at point X, what direction will that cause this system to rotate, the lever arm? Yeah, counterclockwise. It'll go against the direction of the clock, so counterclockwise. What direction would a load at Y cause it to rotate? Clockwise. And those are the two general terms for direction that we use. So whereas we might have had left or right as general terms in linear motion, we have clockwise and counterclockwise for rotational inertia, rotational dynamics. And these things balance in the same way that forces would balance if they were opposite in direction. So if X equals Y, if force X equals force Y, then there is a no net rotational acceleration. Do you see why? They balance, exactly. To some extent, we could think of them as having canceled out. And those are torques. Could I also put torque X and torque Y? Sure, and really that's what we're talking about because we have this distance here, this lever arm L, where if this is the same, these two lever arms are the same, and these forces are the same, then the torques are the same. Because really what we're talking about is torque. So the torque of X equals the torque of Y. This is true only if we consider the lever arms the change, but this is the actual truth here. The torque, if the torques are balanced, there is no change in rotation. Another one. Rotational inertia. Will you remind me what inertia is in general? Or our first... It's almost, I wouldn't say it's the opposite, but it's kind of like the converse of that or something, where it's the difficulty of change in motion. Or we could say an object's resistance to its change in motion. So if we have rotational inertia, it's how much it resists a change in rotation. Resistance to a change in rotation. Think about it if we continue to relate them. Which would be more difficult for me to change its motion? First of all, what is the motion of these two objects right now? Marker, red marker, justice. what is their motion right now? Yeah, relative to Earth's surface, like how we normally use it. How are they moving relative to Earth's surface? They're not. They're both still, right? I mean, I'm kind of flopping this one because I'm gesturing, but they're both still. So how hard would it be for me to start them moving? Which one would be more difficult for me to start it moving? Justice. Why?
Because I'm further away.
No. More mass. Yeah, more mass. More by 1 kilogram. Oh, we're going to have to probably pause this. So the more mass that the object has, the harder it is to change its motion in the term of inertia. And that's, to some extent, that's true for rotational inertia too, because you think about which one of these things would be harder for me to start to rotate, the red marker or justice. Justice. Again, partially because of the mass, but there's another thing too here, and we talk about rotational inertia. So this depends only on mass. Depends on mass. This up here depends on mass. The greater the mass, the greater the inertia. That should be a review. This, though, depends on, well, let's think about it. Would it be, let's look at this little diagram here. And it gives the answer away. But if we look at this one, which one's easier to rotate? It's the same weight. We're considering this to be the same mass. Which one's easier to rotate? The top one. It even says easy to rotate underneath it. But obviously, if the mass is the same, we can't just say depends on mass. Does it depend on mass? Sure. Would it be easier to rotate this top one if it were heavier? No, it would probably be harder. And so it does depend on mass, but it also depends on mass and radius. The distance the mass is away from whatever the point of rotation is. In essence, this has the same mass as this, right? We agree that this marker has the same mass as itself. It would be easier, because it has a lower rotational inertia, to rotate it about this axis than to rotate it about this axis. Do you see? This axis of rotation would be an easier thing to cause it to rotate than this one.
Because there's more weight.
Yeah, the weight is distributed further from the center because it also depends on the radius. Usually with this formula, I equals mr squared, where I is the rotational inertia, m is the mass, and radius is squared. And there we use different coefficients for the mass depending on the actual orientation of the matter. So for instance, this is true, we say, for a pendulum suspended from a massless string. It's true for a hoop spinning about its axis as a hoop, but there's different ones depending on, like if it's a solid sphere, we would use I equals 2/3 mr squared. Basically, the m gets a different coefficient depending on the orientation of the matter, which you don't have to have memorized, but you will be told, like, rotational inertia for a sphere is calculated as I equals 2/3 mr squared. It has this mass and this radius. What's the rotational inertia of that sphere? So memorize this kind of basic one and use it if it doesn't say so. But if you get a specific shape that it wants you to calculate, it'll give you the formula too. There's this nice little, and this, sorry, by the way, this is the reason why if we have two ramps that are the same, and down one is falling an empty can, and down the other is falling a full can, well, a partially full can, these behave differently. So even though we know the force of gravity acting on them will be the same, right? They have the same mass, and so F sub g is the same for both of them. It seems like they should. We know that heavier objects fall at the same rate as lighter objects, right? You remember that. There's a constant acceleration for heavy and light objects. So it seems like these should roll down this ramp at the same rate too. But in actuality, because of the differences in rotational inertia, they don't. A solid cylinder is I equals 1/2 mr squared, and this hollow cylinder is I equals mr squared. So it ends up that for a given mass, the full one ends up with less rotational inertia. It's 1/2 mr squared. And so the full one will go down the ramp faster because it has less rotational inertia. That was kind of a side note. And another little side note is that when I talk about the axes of rotation for this marker, we have those axes named for something like a person, or something that we could diagram in a similar way to a person, where this axis that goes down straight through your middle this way is called the longitudinal axis. Longitudinal axis. And what must all these axes pierce? What part of your body must they all go through? Can you guess? What part of your body must all these axes go through when we're talking about the axes of rotation? They must all go through the center of gravity, or the center of mass specifically. But this axis, this way through you, is called the transverse axis. And then this one that goes like from you to front to back is the median axis. How can I do a rotation about my longitudinal axis? Looking at this diagram, tell me what to do. How can I rotate about my longitudinal axis? Yeah, this is a rotation about the longitudinal axis. Ta-da! How can I rotate about my transversal axis? No. Yeah, flip. A back flip or a front flip, which I can't, right? I'm working on it, maybe someday. But that would be it. Like a front flip or a back flip would be a rotation on the transversal axis. What about the median axis? If I had a little bit more room, I probably could do a rotation about my median axis. No? What? It's this. This is the median axis. How can I rotate about this axis? Yeah, you can. Cartwheel. Cartwheel. Cartwhel. Cartwheel. So those are your axes of rotation. And they're the same for this marker, right? We could say this is like a twirl. Why am even I, your boy, able to do a rotation about my longitudinal axis? No, thank you, but no, it's because this one would have the lowest rotational inertia, just like we said before. Because in each of these cases, I have the same mass, obviously. All it depends on is the radius about which I'm rotating. So for my longitudinal axis, my radius is the lowest, and therefore my rotational inertia would be the lowest. It would take the least torque for me to rotate about this axis. For my, this one's the transversal, takes a little bit more, and the median takes a little bit more, and the transversal would probably take the most of all, at least for me. And then the last thing we're going to talk about is called angular momentum. Can you guess the linear parallel to angular momentum? Well, what do we call, you remember, so like we had linear motion is caused by, a change in linear motion is caused by a force, a change in rotational motion is caused by a torque, that's one parallel. We had this inertia for linear motion and rotational inertia for rotational motion. Do you remember what might be the parallel for this? We're talking now about angular momentum. What was the linear parallel for angular momentum? It was just called momentum. It was just called momentum. So this is the rotational dynamics version of momentum. Remember, momentum was a little bit different from inertia. Momentum, linear momentum that we already talked about this year, was how hard it is to stop a moving object. Only moving objects have momentum. We used P equals m cross v. So as a reminder, regular momentum was P equals m cross v. Remember that one? Now angular momentum is going to be how hard it is to stop a not moving object, but a what? Can you guess? No. How hard it is to stop its angular momentum. We could call it rotational momentum. Yeah, a spinning object. How hard it is to stop a spinning object. Angular momentum L equals I omega, where L is angular momentum. We'll talk about the units in a second. I is rotational inertia. What do we measure rotational inertia? And we had this equation for it. What do you think it's measured in? mr squared. Kilogram meters squared. And then omega, do you remember omega from before the break? Rotational speed or rotational velocity. And that was measured in usually something like rotations per minute, but we really like it to be in rads per second. But remember, the rads are kind of like a pseudo unit. And so we end up with kilogram meters squared per second as our unit for angular momentum. So kilogram meter squared per second. And we just leave it like that. Kilogram meter squared per second. So something can have a larger angular momentum if it has a larger rotational inertia or if it has a larger speed, a larger rotational speed. And the demo for this, and this is the last thing we're going to do, the demo for this, that it must always be conserved, is this. This is our little demonstration for the conservation of angular momentum. Let me get out of the way. I'm just going to do it myself. Sometimes I have kids do it, but then everyone always messes up, so I'm just going to do it myself. So I'm gonna spin a certain amount. How am I going to do this correctly? I thought this would work really good. I have my kind of weighty paper towel rolls. They don't weigh a lot, maybe 5 pounds, but I'm going to hold them away from my body, which is going to change my what? No, well, no. Yeah, the distribution of my mass. It's going to change my rotational inertia because I'm basically increasing the radius about which me as a system is rotating. Okay? This has to be conserved. This must always stay the same for a system. So if this must stay the same, and I bring my arms in, I decrease my rotational inertia, right? Because I'm lowering the radius, and so I'm decreasing my rotational inertia, but this has to stay the same. So what must happen to my speed? Yeah, exactly. So let's see if I can. I'm gonna spin with these out, and then I'm gonna pull them in. Let's see what happens. I'm not either. Look at my little feet go. Oh, that really does do it too. And then I can slow down again and speed up again. Why, by the way, am I not spinning forever? I just said angular momentum is always conserved. Why am I slowing down? No? A little bit of that, but that's a kind of what? Friction. It is a force, it's friction. And interestingly, since it's angular momentum, remember friction is the transfer of kinetic energy to particles. But since it's angular momentum, what's happening is as I spin, the particles in the air that are taking that away and the particles in my chair that are taking that away, they start to spin slightly faster, which still comes out as heat. It's still friction. You have questions about this? I'm going to end the video and then you guys can try this little demo. But do you have questions about anything we did today? This actually, I would say, and I'm not trying to toot my own horn, but that was the best that demonstration has ever gone. Bye! I'm worried this whole time that my mic isn't on. Did it stop? No.